All right, so let's go over the test right now. We're going to go over answers in just a second after. This is what for posterity's sake here. I'm giving Morgan a charger because she didn't bring her own, and now it's on the video to be immortalized on the internet forever. Boom.
Oh,
What's happening?
You don't know. I'm recording right now.
Morgan did not have. Hi, Cass. Hi, Red.
What did you just call
Cass and Red.
Red?
Yeah.
Rebecca.
What do you guys all call her Rebecca? Am I the only one who calls her Mia?
I call her
She
Mia,
doesn't
Rebecca,
care.
me
I know
Becca.
she doesn't care.
I won't.
I've talked to her
actually.
Kill yourself.
Just
Just making sure I wasn't
I've
like
heard those
violent.
three.
Alright, very good. Okay, so multiple choice answers. Are we ready?
Sure.
First three are blah blah B.
Okay.
B, B, and B. 4, 5, and 6 are A, D, and C. 7, 8, 9. Guess who's back? Back. B, A, C. Right now it's back. Tell us.
7, 8, 9.
B, A, C. For 7, 8, and 9. 10, 11, 12. B, C, A. No, I just Lex Dixit you. Sorry. 10, 11, and 12 are not that. They are C. Did I say CBA?
B
said BCA. I know, that's what I thought. Yeah, okay. The correct answer is 10 is C, 11 is B, and 12 is A. And 13, 14, and 15 are do 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 do. Dad. Oh, I did think.
It was really clever. I see what you did there.
So once again, 1, 2, and 3 were blah blah blah. 4, 5, and 6 were A, D, and C. 7, 8, and 9 were back, B, A, C. 10, 11, and 12, because I screwed up last time, I'm going to be very specific here. 10 was C, 11 was B, 12 was A, and 13 through 15 spelled dad. I don't see mom on this. Alright. Let's go over the multiple choice. It's going to be hard for people online to ask for particular questions. If you guys have individual questions that we don't cover, please let me know later. Number 1.
Yes.
If something goes down to 75% its original value, by what fraction did it go down?
3/4.
3/4. So how much would magnetic field have to go up so that it stays the same?
25.
4/3. 3/4 times 4/3 will get you 1. Magnetic flux is B times A times blah blah blah, but we're not worrying about that. It just said the area went down by 3/4. Yes? And it said flux stayed the same. In order for flux to stay the same, how much does B have to increase? By 4/3. How much of an increase is that? 33%. All right. Number 2.
Yep.
Okay. A double loop of wire. This is going to be like 1,000 times almost this exact same example. A double loop of wire is placed on the XY plane. So for sake of argument right now, in the example, you guys can't see this in class. Well, no. Let's make it so that online people can see it. All right.
It's not
Our podcast.
Yeah, I'm not going to podcast it. So here we go. So we're going to say the XY plane is the screen that you're looking at here. So we're flipping a little bit of perspective here with some examples that we'll do later. But a uniform magnetic field is increasing in constant rate in the positive Z direction. Now this is where that kind of direction thing really matters. If I draw XY up here, in what direction is Z? Try it again. Out at you. Remember? Positive. Z is directed out at you. Yes? You're good on that? Okay. A uniform magnetic field is increasing in a constant rate in the positive Z direction. So that means the change in magnetic flux is out at you. So the induced should be, sorry, hold on. Yeah, which way should the induced be then? into the board. So yeah, negative z direction is correct. Number 3.
We said the correct answer was C.
So the correct answer was B.
The B, okay.
1, 2, and 3 are all B.
Yes.
A circular loop of wire has a radius reduced in half the time in delta t. A uniform magnetic field has an angle of 60 degrees to the plane of the coil of the wire. The magnetic field doubles its intensity in the same interval delta t. During this interval, what happens to the flux going through the wire? I'm going to make sure I say this again. So the circular loop has its radius reduced, which means area decreases, right? In half. Now, if radius cuts in half, what's area cut in? A fourth. So, I think this is what I want. Is this what I want? It's not what I want at all. We're doing flux. No, hold on. Am I looking at the right one? Oh yeah, we're looking flux anyway. What effect does time have on flux? None whatsoever. And it tells you an angle, but does the angle change? So the only thing that matters is area. Area decreased. So it doesn't even matter if 1/4 versus 1/2. Area is the only thing that's on this that does affect it, and therefore it should decrease. 3 loops of wire, 1 circular, 1 rectangular, and 1 square, all made from identical lengths. Okay, so this is a hard one. This is a hard one. So we'll cover this here real quick. Okay, now you can intrinsically know which shape automatically gets the most area, possibly through math and discovery stuff later, but I'll do the proof in just a second. So 3 loops of wire, 1 circular, 1 rectangular, 1 area, all made from the same length of wire. If the loops are placed in the same increasing magnetic field, which loop will have the greatest induced EMF? That should be the one with the greatest area. So this is actually a little bit of a geometry problem, and it's which one's going to get us the most area. So let's start off with square. Okay, and I'm going to make my life easier here by saying that the amount of wire they're using is the same. So I'm going to pick the amount of 4L. That's how much length the wire is. The reason I do that is for this square, that means each side, of course, is L, right? Which means the area that this one can create is L squared. Cool? Cool. Let's do a rectangle. Now, I think you can kind of see it, but essentially, here's what we got. We have that the whole thing is 4L, and I'll call this, let's just focus on one side, okay? Focusing on one side here, this side will be L plus X, just X being some random amount extra, which would make this side over here L minus X. Does that make sense? Basically, if I took X, if I took X from this amount here and put it extra over there, this side's going to be longer, this side's going to be shorter, but by that amount, right? So then the area becomes, let's see, that would be just these two sides together, L squared minus 2XL minus X squared. Now, what does that tell me? Well, that tells me for any amount of X whatsoever, for any amount of X, it's going to be smaller than L squared, right? Do we see that algebraically? There is a way of doing this, by the way, with calculus as well. But so far, our greatest area is the square. Let's go to the sphere. Arguably sort of the easiest, but the circumference, I said, was 4L. But what do we need in a circle in order to figure out its area? We need to know radius. How do we get to radius here? Circumference is equal to? You forgot circumference.
Yeah.
2 pi r.
2 pi r, thank you. Which means radius is going to equal, if that is 4L, cancel, cancel, 2. That's going to be 2L divided by pi. Yes? And area is what? So that would be pi times this mess squared. Now that's going to get us 4L squared over pi. Because that pi squared cancels with this one over here, and that all becomes 4L. Yes? So now, to compare, I just need to do a very simple thing. And that is, compared to this guy, L squared, here's my L squared. What is 4 divided by pi? More importantly than that, you don't need to punch it in your calculator. Is it greater than 1? Yes. So which of these up here has the greatest area? Circle. So which one will have the greatest flux, thus the greatest EMF? The circle. According to Lenz's law, the direction of induced current in a conductor will be that which tends to produce which of the following effects? Oh, sorry, do we need 5? Yes, no on 5? Nope, okay. 6. A coil is placed in a changing magnetic field and EMF is induced. What happens if the induced EMF, the rate of change, quadruples? You look at an equation and here's what it just asked. Hey, what happens to this if this goes up by 4? It goes up by 4. Yeah. If that goes up by 4, that goes up by 4. So it should be what? C, right? Okay. Do we need 7? Okay. So it's saying a bar magnet is falling through a loop of wire. So I'm gonna for the sake of people watching the video, I'm gonna use a loop of wire right here. Now, if it's me, what I would probably do to just kind of imagine this somewhat correctly is I would imagine a loop of wire on my desk and the object obviously moving at it straight downward. In my picture up here, you can look at it however is easiest for you. In my picture up here, this technically means which way is the magnet going? Into the board. Yes, it's coming out. And here you go. Here is the direction of the magnet. All right. A bar magnet is falling through at a constant velocity. The south pole enters first. Okay. You are very used, because this is like what all of the examples are. You are very used to magnetic field being like this. Is that always the case? As a matter of fact, if the south magnetic pole is what goes in what direction in this picture would the magnetic field be pointing? What's the rule with magnetic field and bar magnets?
It goes
out of north. So if north was going in, that's what we would see. But since it's south, the direction of magnetic field is this. It's out of the page. Okay? Should magnetic flux be increasing or decreasing?
Decreasing.
Try again.
Increase.
Why should it be increasing?
Because
Where's
it's going toward
where is the strongest magnetic field?
right next to south, right?
So as the south approaches, should magnetic field be getting stronger or weaker?
Strong.
Stronger. It should be growing. So it's weird to think of this because, again, you're used to it being into the board, but the arrow is out of the board here, right? And it's getting more out of the board.
It says as the magnet leaves the wire.
Oh, my apologies. My apologies. I don't think I read that. Yes, you are correct. I'm sorry. I apologize. You're 100% right. I was tracking it as though it was headed towards it. So you're right. In that, so it's still out of the board, but because of what you said, magnetic field should be getting less, should be decreasing. So here we go. Arrow is out, changes. The change in flux should be which way? Which way?
I thought it should be like this one, right?
So the arrow is out. So I'll
Oh, the arrow is out, then it should be
but
that
the
way.
arrow's getting smaller, so the change is
It's this
in.
one, yeah.
So the induced is out,
Ow.
because it's the opposite of the change. So that means it should be counterclockwise, yes? 7 should be B, all right.
Okay, wait.
Yes. Let's do that again. Here it is. Okay, I'm going to draw a different picture to help. Let's take the same one from the side. So here comes.
No, I get it now. I just did it. I turned my paper. It was weak. Because
I just want to make sure and do it myself here. Okay. So here's south. It's going that way. Okay. So the magnetic field leaves south. So it would be like this. Okay. This would equate to out of the board over here. Okay. So the magnetic flux. Let's use different colors here. The magnetic flux is out of the board, but it's getting smaller. So the change in magnetic flux is into the board. So the induced magnetic field should be out of the board. That should have been induced in D. Therefore, on this, if flux is out of the board using right-hand rule, current should be that. Okay. Numero 8. Sorry, 8. A bar magnet is falling through a loop of wire with a constant velocity of the North Pole enters first. The induced current will be greatest in magnitude when the bar is located where?
Near the south.
Yes, either north or south.
Either north or south, it doesn't matter.
That's the strongest of both.
Yeah, the size doesn't matter. As a matter of fact, when you look at this picture over here, if I have a loop of wire like this, let's draw this at 2 separate times. Okay, here's the north, and I'm assuming it's going to the left in this case. Does magnetic field even change direction? No, because on the left side it's pointing left, but you're heading at it, and on the south side, as it passes through, it's heading left, but you're leaving. Yeah, it's still.
So
it's to the left.
Near the North Pole.
It should be either north or south. As the loop either nears either the north or the south.
Oh, okay.
Middle of the magnet would actually be where it is weakest. The poles, by definition, are where it's strongest. All right. Do we need 9? Do we need 9?
Yeah.
Yes? Okay. So we have a plane here. Doing the best I can. Here we are. Nailed it. Okay. And those wings, so this is the side view. So we'll go with like my top view here. Okay. Those wings are like a long metal rod. Okay. The airplane is traveling, let's see here, wingspan of 79 meters. What should that be? That would be the length of them. Okay. At the point where downward component of magnetic field is 0.49 Tesla. So the velocity is this way, okay? The direction of, let's use a different color actually there. Here's velocity, okay? And what it just told you is that the downward direction of magnetic field is, and that would be into the board here. This is a top view. Should be, what was it I just told you? 0.491 times 10 to the negative 4th Tesla. And the induced potential, EMF, let's use another color entirely. EMF is some number, doesn't matter. Well, it's over goes, 0.875 volts. And the question on the table is, what's the object speed? Here it is in a nutshell. What do I do? There it is. So you should take 0.875 divided by, what's the tiny number at? 4.491 e to the negative fourth times 79. I got 225.5 or 226. Is that the answer? It's 9C. Huzzah! Do we need 10?
Yeah.
Okay. Metal rod is falling towards the surface of Earth near the equator. As it falls, what does that tell you, by the way, when it says near the equator?
Magnetic flux.
Not
Or
magnetic flux.
field.
Field. Magnetic flux is perfectly north. So as it falls, one end of the rod becomes positively charged due to motional EMF on the rod through the Earth's magnetic field, aka it's just basic right-hand rule. So here we go. Let's go ahead and say your direction that you're facing is north. Okay, so here's north. What's the direction of velocity? Velocity is straight down. So take your hand, turn magnetic field right. You'll notice your thumb is pointing right. That means what are the positives going to do? Go to the right, which is what direction? East. East, correct. So the answer should be C, right? Yes. Do we need 11? Do we need 11? Yeah. Okay. Number 12? Yes. Basic function of an electric generator is what conversion process? Mechanical energy to electric. Yeah. You use mechanical energy to spin it. And now you might convert something into mechanical energy. For example, a standard generator that you have outside, what do you use to get it running? Gasoline. So you would use chemical energy to create mechanical energy to create electric energy. The reason why we wouldn't begin a chemical is because, as we've mentioned in here, there's a bunch of type of generators. There's hydroelectric generators, there are wind turbine generators, there are nuclear generators, there's coal generators, but the gist is all the same. You take a loop of wire, you spin it, mechanical energy. Now the means by which you spin it can be different, but find a way to spin a loop of wires and you yourself will make electricity. You have a loop of wires, okay? You have a loop of wires and a magnet next to them, and you just decide to spin it. You yourself are now a generator. You can power something, probably not much. All right, number 13.
Yep.
Boo! Why does back EMF get created in a motor? We just basically talked about it. There's a loop of wires spinning in a magnetic field, right? So when are you going to get the most back EMF? When you get the most magnetic flux. So when would that occur? When the motor is spinning at maximum speed, correct. Motor spinning at 0 will not create any back EMF at all because nothing is spinning at all. Voltage and current go hand in hand when one is the maximum, the other is the maximum. So if you have both of those answers, A, neither of them could be correct, but also you're not going to get the maximum voltage because you have back EMF. Back EMF is going to limit that voltage. The most voltage and current you're going to get is when it's spinning, but it's spinning the slowest because you're not going to get very much back EMF at that time. 14. Electricity may be generated by a rotating loop of wire between the poles of a magnet. The induced current is greatest when the plane of the loop is parallel to magnetic field. The plane of the loop is perpendicular to the magnetic field. The magnetic flux through a loop. It's just basically this. If I have a magnetic field that looks like this, and I have a loop of wires that looks basically, I'm just going to draw it from the side view like this, your options are, actually, let's go back real quick. I want. Is that good? Okay, let's draw this 3 times. Actually, let's make my life easier here. Copy, paste, paste. Oh no, it's not good. Mistakes have been made. No, stop it. Let's try one more time. All right, here we go. Let's try this now. So we have 3 magnetic fields. Okay. It doesn't matter that the middle one has no flux in it whatsoever. What you want to think of is this. Okay? If I change a certain amount of angle in all of these, which is going to create the greatest change in magnetic field? Now, magnetic field in this particular case, magnetic flux rather. Magnetic flux can change between one of 3 reasons. There is the size of the field, which is not changing here, forget that noise. The size of the area, which is not changing, forget that noise. But the orientation. Or another way to look at that is what you want is you want magnetic field and that area to be perpendicular, right? So, in which of these angles does the greatest amount of perpendicular area change? 2. That's going to be 2. If I drew this correctly, which I don't think I did, this one's going to change by this much. Which one of those areas just changed? Definitely the most. Now, obviously, this is done by hand, but yeah, essentially, it's going to be the second one. And the reason so some people get stuck on that because the weight, that doesn't have flux. But keep in mind, this is a limitation of drawing a picture versus drawing an animation. If we were looking at this in an animation, as it was actually in the process of moving, what we'd want to see is how much it has changed. It's going from 0 to some value, and this value in the middle one is going to change the most. So it should be A, yes? Is that the correct answer? Yes. Hey, how about that? Getting lucky here. Do we need 15?
Yeah.
Okay. So we talked about this a little bit with back EMF. Essentially, the way you can think about it is this. You've got a motor that looks like this, right? This is when it's not running. Because if it's not running, as we said a second ago, there's no back EMF. It says the wiring in the motor has a resistance of 1.2 ohms. 2 ohms, okay? And it is connected to a 10.3 volt battery. And essentially, back EMF can be seen approximated as a battery pointing the wrong direction or pushing against. So it says this is 0.62 volts. So how do you get your actual voltage? Yep, 10.3 minus that 0.62. You get 9.68. Divide then by 1.2, and you should get that it's about, I got 8.06, 8.07, so I got 8.1 D, yes? Ooh, I can't do this on the recording. Well, I can. Okay, so I am going to, these are my problems here. I'm going to try to do 1 and 2 in such a way that basically I can set them up the exact same way because it is practically the same thing. Actually, arguably, no, not quite the same thing as number 3. But here it is in a nutshell. You are given some value of n. You are given, and then you're going to basically get EMF is equal to negative n times the change in magnetic flux all over delta t. So in case of 1, you are given n, you are given a length in order to get area. Keep in mind, once again, 2 centimeters squared does not convert to meters squared by dividing by 100. A couple of you in here. It converts to area by dividing by 100 squared. To see that work here real quick, that is 2.1 centimeters squared. If I want to convert it over, you can use 100, but that is the linear That is the linear thing. So to get the area one, just square everything. So this 4.1 centimeters squared will actually become, I think it's 4.14 times 10 to the negative fourth meters squared. Yes? Next, given to you is that the magnetic field is constant at 1.5 Tesla and 31 turns, and resistance is 0.780 ohms. First thing was EMF, and here's what I would suggest. Negative N times, I think, what was changing? Oh, it's technically angle, isn't it? Yeah, it's angle, because area doesn't change, and that's right. Area doesn't change and magnetic field doesn't change. So what I would usually do here then is this. I would say magnetic field final minus magnetic field initial. Which one cancels? I'll give you a hint. It looks like this at the beginning. Is there currently magnetic flux?
Yes.
Yes. So in the end, why is there no magnetic flux after it's turned 90 degrees?
Parallel.
It's parallel. So yeah, that means final should be 0. Now I think this happened to one person, but they accidentally put negative on this and should not for 2 reasons. The first reason of which is you can notice if you do the math correctly here that the negatives will cancel, but even if the negatives didn't cancel, if you look at the problem carefully, it says right here the magnitude. So even if you did get a negative, you would have ignored it when putting in your respective answer. So here we go. How do I get this? Cancel out the negatives. It should be N31 times magnetic flux, which is going to be 1.5 Tesla times 4.14 times 10 to the negative fourth meters squared, all over the time of, I think it tells us the time. Well, I didn't write it down, but it tells us. Is it 0.335? Not 0.355 there, Lucas. Okay, time is 0.335. And Lex Dixie is hitting everybody today. Okay, so 0.335 seconds. And I'm just going to skip to the right answer, which is in milli, 61.2 millivolts. And easy peasy stuff to finish. Current is equal to voltage over resistance. So 61.2 millivolts divided by 0.78 ohms should give you 78.5 milliohms. Questions, concerns? Cool beans. Next one. The major thing that I love about number 2 is that there is no 0. There absolutely is no 0 in this case, and nothing actually cancels out. So I'll just go back and use the exact same stuff, okay? Because I think pretty much it gives you everything. The only thing I would change, well, let's change everything. Hold on. Once again, we have to convert. Instead of this 2.5 centimeters, it straight up tells you that it's going to be 200 centimeters squared. But once again, 200 centimeters squared, we do the 100 centimeters is 1 meter, but we square everything. So the area is 0.02 meters squared. Number of turns is 190. So that's 190 now. Rotation, there's rotation or no? Oh, no, but it tells you it changes in 0.2 seconds. The resistance was, where are you at? 7. This is just 7. And the one major thing that's different here is instead of just saying magnetic field is 1.4, this would be what it is initially, right? Which means, what is it finally? Now the exact direction on that, actually I should check this real quick. Yeah, it says upward and downward, so it doesn't really matter which way you define as positive or negative. It's entirely up to you, but you do have to address them differently. Can I help you find something? Yeah, you're in the right spot now. So instead of canceling right here, actually, let's do this differently entirely. Let's take you entirely out. Where are you? There we are. Trash it. Okay. And this right here I would write down as negative n times change in magnetic field times area over delta t, or negative 190 times, what's final? I think I actually did negative. It doesn't matter if you said positive as long as the other one is flipped. Okay. And then I have minus, because that's how you get the change in, and it's 1.4 Tesla. Now, again, order doesn't specifically matter. So the general thing I looked at on your work is this. Did I see 2.8 here, right? However, it changes positive or negative, even if you kind of worked that out ahead of time. Okay, boom, divided by 0.2 seconds. And then, of course, if we really want to make our lives easier, let's do this. Current is equal to EMF over R. So this whole thing over R. So this whole thing over R. So this whole thing over 7 ohms. And if you've done it correct, I think you get 7.6 amps. Questions, concerns? How do we feel now?
Frustrated because I literally did this. And then
You
I
did.
second-guessed
Your
myself.
mistake was this right here.
I know.
Yeah. Now I don't think I took off any points for how you did it the second time, because I know you did it right, and I think I just took off for the mistakes that you made the first time. So there is that. All right.
I got exactly half the right answer.
Well, that would be because the very important thing.
Yeah.
That's one of those is not zero. That's a really important thing here. All right. And finally, let's talk about this guy. Now, the first two are actually relatively easy. While the concepts are hard in that you can do this whole thing, you can say, hey, magnetic field is down, velocity is that way, so there should be a force this way. That force, as we said quite a few times, we approximate as like a battery or an EMF. And there is a straight up equation for part A. Nope. I skipped ahead of myself. Mistakes are being made. Don't judge me. Or do. Your call, really. I talked about this Morgan last year. Sometimes judgment is good. It's good. It keeps you on the right foot. Okay, not entirely, but all right. EMF is equal to BLV. Basically, you're just plugging and chugging it. Right? B is 0.8. Length is 1.37. 1.37 meters. And velocity is 2.85. And the whole goal of this was not to get EMF, but to get current. So if you want to just take it one step further, current, once again, is equal to this divided by R, this divided by R, so this divided by 0.4. And if you've done it correctly, you should get about 7.81. And part B, once again, if there is current moving in a magnetic field, there should be a force magnetic, which is this whole thing. And nicely, this is once again just a plug and chug equation. B is still 0.8 Tesla. Current, we learned from the last problem, is 7.81 amps. And length is 1.37 meters. I'm realizing as I'm writing this down that I don't know if I checked for some of you guys that answered A wrong if you did B correct. So if you're pretty sure that's the case, show me in just a bit. I'll make sure that I didn't take off points when you did that particular part correct. See if you can't humor me though with this real quick. This answer, by the way, just real quick knocking it out, is 8.5756 newtons. See if you can't humor me real quick. What is the direction of that magnetic force on the bar?
left?
Well, it depends on what angle we're.
No, it very much does not.
Is it to the left?
It's definitely to the left. Look, it's right hand rule. I'm telling you.
It's the opposite of velocity. What's the direction of current?
Oh, it's just like back.
What is the direction of current in this guy right over here? Well,
it goes from B to.
It goes from B to A. So over this guy over here,
So
it goes
then-
this
Clockwise,
way.
kind of.
So let's
Clockwise
say that's
is
out
the
at you. That's out at you for the sake of argument. Which way is magnetic field?
Down.
So force is resisting the direction of velocity.
Wait. But this right hand rule that you just did. said
Okay.
it was-
Careful here. There's two right-hand rules going on, which is why we try to talk here. There is a right-hand rule that causes the EMF that we are discussing. If I just use the red velocity right there and I point this way, okay, and magnetic field is down, that would put a force out at us. But that is what causes this. That's what causes the current to go around. Yes? Now there is current. As you can see my finger going up here, sorry for people online, okay? You can see the way the current is going. So if I go over to the wheel, you'll notice that the current is going. Let's just pretend that's out at you for sake of simplicity. That current is like a movement of positive charge. So out at you. Direction of magnetic field is down, so the force should be back. Okay? It's a little bit weird because of the perspective here, and if this ever happens to you, I highly suggest that you're like, hey, I'm just going to draw it from here is the wheel, and recognize that current would be coming out at me. So if current is coming out at you, and then you point magnetic field is down, that would mean that the force using the right-hand rule that you just said should be this way. Make sure I'm right there. Yes. That way. Or if it helps, like we've shown several times, it regularly resists the motion of the object. Meaning that if you don't have this is actually really cool. Watch this. Okay, if you don't have a force propelling it to the left, okay, let's say there is a velocity to this way, okay, what should naturally happen to this wheel that the magnetic, what would it do? If force always goes the opposite of velocity, what should that magnetic field cause the thing to do? Slow down. Which is why we have such thing called magnetic brakes. Magnetic brakes are regularly what is being used at Six Flags because it causes way less friction and heat, and instead just causes to stop. So like if you were, I don't think Superman's not a thing anymore, but if you ever rode Superman when it fell, they have Catwoman in its place. It's really cool. Highly suggest. Though it's a little bit loopy. Anyway, you guys were there last year. There were giant magnetic fins. There were giant, basically these metal fins on they were magnets, yeah, on the outside, and all you had to do is put like metal fins on excuse me, on Superman, and as it ran through the magnetic field, as it goes through the magnetic field, it will cause it to stop. And the nice thing is, the faster you go, the more force it puts out, so the more acceleration, the quicker it brings you to a stop. This is also how almost every single roller coaster is stopped. I was going to say started. That's not true. Is with that. By the way, the railgun technology that we've been talking about here, that I showed you kind of over here, is exactly how Mr. Freeze starts. As a matter of fact, if you heard when we used that the other day, there was like a buzzing before it shot off. Not quite at that level. You can hear that buzzing actually in Mr. Freeze if you're sitting there right before it shoots you out. And that's what that buzzing is a lot of current going through a system, propelling you, showing you in that way. I don't know if I've told you this story about Mr. Freeze, so I'm going to take the time to do it real quick. I apologize for repeating myself. Mr. Freeze uses so much electricity. It's insane. It's insane how much. When they first did Mr. Freeze, they had essentially, you know, those big those breakers that see these like giant areas of like a whole bunch of electricity transformers over in a spot like when you go past a town. Okay, so that's essentially like one big circuit. All right. It used to be that before Mr. Freeze, Six Flags and the town of Eureka next to it was on basically the exact same one of those. Okay, makes sense. It's not exactly that big of a place. You should be able to run it along with a small city and be okay. Then they turned on Mr. Freeze once, and everybody's power went down because of how much electricity it pulled. All right, so all right, we'll fix this. They essentially put Eureka on its own breaker, and they put Six Flags on its own breaker. They ran Mr. Freeze again, and Six Flags electricity went down. So now there is essentially a giant breaker for Eureka. There is a giant breaker for most of Six Flags, and there is an own independent breaker for just Mr. Freeze because of how much electricity it pulls. All right, back to this guy right here. So you've probably already seen me do it. Which side should be the high side? This should be the side that is pushing to the other side. And there's two ways to look at this being B. Okay, the first way is what I did just a second ago, and that is just to use the right-hand rule to see, hey, velocity is to the left, right? Magnetic field is down, so the force on it should be pushing this way, right? So if it's pushing this way, we come over here and it's pushing from B to A, so B should have the higher potential. Make sense? The second way that you can look at it, and I don't care either one, I'm only going over both of them because reading your guys' examples, reading your explanations on E, I know for a fact that like people thought this different way. The other way that you can look at this is in terms of magnetic flux. Okay, magnetic field is pointing down. Since the wire or the thing is going in, that means the area is getting smaller, right? Which means magnetic flux is down and should be increasing, decreasing? Decreasing, which means the change should be up, which means the induced should be down. If you do that, what you should see is that the current comes around here in a clockwise fashion, also showing you the exact same thing we saw before. Cool with that? Now, for D and E, should it switch directions? The answer is no. Why shouldn't it switch directions? Let's use both arguments and imagine this guy has passed over. For starters, if we use the first explanation, I think Lucas, this is the one I was commenting on, that you're the only one that got right. Okay, the velocity is still in the same direction, magnetic field is still in the same direction, so the force on this thing should still be in the same direction, right? Meaning, let's copy this picture so I can draw on it. Meaning, when the thing goes to the other side, when this goes over here, the velocity is still this way, right? Magnetic field is still down, so the force, let's do blue here, which over here was this way, is still the same direction, right? Which means current should go here, and current should go there just like it did before. It should not swap sides. Does that make sense so far?
Why did the current, can you re-explain? Can you say it again?
Sure. All right. Do you see how in the first case, come on. Let's just focus on the right side. So velocity is left, magnetic field is down, so the force should be along the axle going this way. You're good with that?
Yes.
Okay. If the force is going along the axle this way, that creates a current that looks like this. You're good with that? Okay. Now, if I go back to the other side, my velocity is still this way, same as it was before. Okay. My magnetic field is still down, same as it was before. So the force that's acting on it should still be the same direction, same as it was before. But now that the guy is on the other side, the loop that would be created looks like that. Is current still going the same direction through the resistor? Yes.
Yes. Oh, because
It's still starting on the B side, still starting over here and going to the A side, so B should still be the, okay. Now, let's go to the other example I said a second ago. It's definitely the harder of the two. I would say that's probably the easiest way to see it, okay? But over here, we said, let's erase, erase, erase. We said magnetic field is down, right? Therefore, magnetic flux is down. But since area was decreasing, magnetic flux should be decreasing. Yes? And therefore, the change should be up. So the induced magnetic field should be down. And if I use right-hand rule, that means that the current should be going clockwise. Yes? You cool with that? That color was not helpful. Are we cool with that explanation so far? Now, as the axle rolls past the resistor, magnetic field will not change direction, but area is now increasing. Since the area is increasing, that means magnetic flux is increasing or changing down. The change in magnetic flux is down. So what should the induced magnetic field be? Up. Which means it should, instead of going clockwise, go counterclockwise. Except now that we are on the other side of the wire, counterclockwise looks like this. So if you look at the resistor, again, that color is unhelpful. If you look at the resistor, is it still going the same direction on the resistor? Yes. Questions, concerns?